suggests that you may know friends. Have you ever wondered how Google Maps can take you from point A to point B in the quickest time possible? Or how Facebook, Instagram, and other social media sites suggest that you may know specific people? Hey there, my name is Uma, and in this video, we'll be talking about Dijkstra's algorithm and its application to software services that we use every day. Let's jump into it. Simply put, Dijkstra's algorithm, also known as shortest path algorithm, is used to find the shortest path between nodes in a graph. Don't worry, I'll break it down. In a graph, we have nodes. The nodes are connected using edges. Depending on the type of graph, the edge might have a weight. Think of this weight as the cost of going from one node to another using this edge. Okay, now that we have that out of the way, this is our graph. Suppose we want to go from node C to node E. What is the shortest path to get there? And by shortest, I mean the path with the least cost based on the cumulative edge weights. Well, there are multiple ways you can take to go from C to E, and they all have different costs. We can go from C to B to E for a cost of 8, or we can go from C to D to E for a cost of 9. We can also go from C to B to D to E for a cost of 19. We can go through all the combinations until we find the smallest cost. This is easy for a graph that has 5 nodes, but gets way more complicated as we increase the number of nodes and edges. This is where Dijkstra's algorithm comes into play. The algorithm is pretty straightforward and goes like this. We keep a list of all the nodes in the graph and the distances from our start node. The start node is C, so the distance from C to C is 0. Since we haven't visited any other nodes, we mark the distances to those nodes as infinity, the biggest number possible. From the start node, we evaluate the cost to visit all the surrounding nodes or neighbor nodes. The start node is C, and its neighbors are A, B, and D. To visit A from C, it'll cost 1, so we update the cost to 1. To visit B from C, it'll cost 7, so we update the cost to 7. And to visit D from C, it'll cost 2, so we update the cost to 2. We have evaluated all of C's neighbors, so we mark C as visited, so we don't go back to it. We then pick a new node from our list of unvisited nodes with the smallest value. In this case, it's A. We move to A and do the exact same thing. From A, we can get to B and C. Since we have already visited C, we can ignore it. However, to go from A to B, it'll cost 4, because A has a cost of 1, which we got from the initial step from C, and the edge to B has a cost of 3. The whole point is to calculate the shortest distance from C, so we must add up all the previous steps. 4 is smaller than the current value of 7, so we update B's number to 4. So if B was the ending point, you're better off going to B from A because it has a smaller cost. In our case, E is the ending point, so we keep going. We mark A as visited since we have evaluated all of its neighbors. We then pick the node with the smallest value from our list of unvisited nodes. In this case, it's D. From D, we can get to B and E. To get to B, it'll cost 7, and since 7 is not less than what we currently have for B, we don't update its value. To get to E, it'll cost 9 because D has a value of 2 and the edge from D to E has a value of 7. 9 is smaller than infinity, so we update E's distance and mark D as visited. We repeat the process and pick the smallest unvisited node, which is B. Now, D has been visited, so we ignore it. E has not been visited, so to get to E, it'll cost 5. 5 is smaller than 9, so we update distance to E and mark B as visited. Finally, we have E. Since all of E's neighbors have been visited, we mark it as visited, and that's it, we have our answer. To go from C to E, the smallest cost is 5, and we will have to go through C, A, B, then finally E. The algorithm also shows the shortest distance from the start node C to all the nodes in the graph. Now, you might be wondering how this relates to Google Maps or social media suggestions. Well, our example has node and edges, but we can think about the nodes as addresses or places and the edges as roads. The weight on the edges can be the time it takes to travel through that road, taking into consideration the number of lanes on the road, the number of traffic lights or stop signs, speed limits on the road, and several other factors. Google Maps already has that data from the road scans it does frequently. It also collects data from users who are actively using Google Maps for navigation. This is how it's able to tell you if there's a congestion or a holdup up ahead and how it can recommend alternate routes for you to take. It continually does a version of the algorithm trying to find the quickest way for you to go from point A to point B. A similar process also happens on social media platforms. They have your profile, your friends, and people you follow. They also have information about what you and those people have in common, like your location. Maybe you went to the same high school, college, you have the same interest or the same group of friends and more. Throwing all this information into our graph, it's pretty straightforward for the algorithm to run multiple times, trying to find the shortest link and suggestions between you and your friends' friends based on things that you all have in common. There are other applications of Dijkstra's algorithm, like in robotics in warehouses, where the robot has to figure out the fastest and most efficient way to get from one point to another one, and in IP routing protocols, where we need to find the shortest path between two computers when you're browsing the internet. I made a pretty interesting video about this, and you should check it out if you're interested. Those are just a few applications, but I'm sure you get the gist of Dijkstra's algorithm now. Simple, efficient, and straight to the point. That's it for this one. Thanks for watching and see you next time. Peace.